code in and then say, okay, so welcome. So here we are. And last time we did this freehand because I'd marked up the notes. So today I can actually show you the notes, the way they're supposed to be without being marked up. What we say is, so here's a point source of charge, and basically we're going to consider a point that's some distance from the point source of charge. So this is a sphere, and that's going to be my Gaussian surface. Remember, the Gaussian surface you decide upon. You decide what shape it's going to be, and you decide where you're going to put it. But I used a symmetrical Gaussian surface, a spherically symmetrical Gaussian surface. And I did that for two reasons. One is that the electric field is going to be constant at a constant distance from the point source of charge. And the second is that because the electric field is radial and because the area on a surface of a sphere is radial, the area vector is radial, these two guys will be parallel to each other. So it simplifies my math. So we say there is a general relationship between the net flux through a closed surface, that's a Gaussian surface, and the charge that it encloses, and we're going to derive that now. That's what we're doing, Gauss's law. So when E is parallel to dA, we can say that E dot dA, which we talked about last time, well, it's going to be E times dA times the cosine of the angle between, which is 0, which equals E times dA. So that's nice and simple. We're no longer dealing with vectors, we're dealing with scalars. So if my flux is equal to the area, the surface integral of E dot dA, it's equal to basically the integral of E. Well, I can take the E out because it's constant, so I get E integral dA. And they actually, because I did that, I've kind of skipped a step here. And this equals, because I can go from that dot product to that magnitude, I don't need these guys here. Okay? I'm actually getting rid of those. It's just the magnitude of the electric field times the magnitude of the area. And then I say, well, look, E is equal to KEQ over R squared. I know that from Coulomb's law. Coulomb's law. So I know that, and I also know that the area equals 4 pi r squared. So I can shove those in, and I say, well, instead of E, I'm going to have KEQ over r squared. And instead of A, I'm going to have 4 pi r squared. And so I get that the number of arrows, the flux, is equal to 4 pi KE times Q. And then the next little thing I've got to remember, and electrical engineers know this very, very well, is KE is equal to 1 over 4 pi epsilon naught. 4 is a constant, pi is a constant, epsilon naught is the permittivity of free space, so that's a constant. So this is just a more fundamental constant than this is. They're both constants. It's just how deep do you want to go? How fundamental do you want to get? But what that does is it means that, oh, hold on. I have, so this is equal to, well, let's have a look. Substitute for KE. 4 pi Q over 4 pi epsilon naught. So the 4 pi's go away, and I end up with Q over epsilon naught. And this is that Q. So this is how we decide how many arrows we imagine been drawn. There's so many you couldn't draw them. But we say the number of arrows, my flux, is equal to the amount of charge I have divided by this constant. So it's a way of scaling our imaginary diagrams. So we define Gauss's law, and Gauss's law says flux is equal to the surface integral of E dotted with dA, and that equals Q in over epsilon naught. And so there's really two, there's three bits, I guess, to Gauss's law, and sometimes we'll combine these two, and sometimes we'll combine these two, and sometimes we'll combine these two. So get used to writing down Gauss's law completely, and then you'll find that sometimes some questions can be quite easy, and here are some relatively easy questions. It says, okay, you have a weird shaped Gaussian surface, and you have 3 charges inside, 3 positive charges, and we want to know what is the flux. Well, flux is equal to the surface integral of E dotted with dA, which equals the Q inside the Gaussian surface divided by epsilon naught. Clearly, this bit's of not particularly value to me. I know the Q inside. I know epsilon naught. So this is simply 3 over epsilon naught. And the units, well, it's still going to be newtons per coulomb meter squared because it's still going to be, flux. So, now think of it. I'm a teacher. I can make this like a really involved shape. I can either make it so weirdly non-uniform that it puts people off, or I can actually go the other way and make it weirdly structured, so it's tempting to try and work out volumes and surface areas. I'm trying to hey, play with this. But the fact is, all you need to know is what's the Q inside and divide it by epsilon naught to get the flux. Okay? So don't get fooled by that. And now we just move the Gaussian surface over to one side. And so we find, well, okay, the flux is equal to Q inside over epsilon naught. We look inside and there's no charge inside. So we have no arrows. Well, hold on, what's that? That's an arrow. Oh, yeah. But it enters and it leaves.
It doesn't originate inside, so it doesn't matter.
Does not originate inside. So the net number of arrows is 0. One comes in, one goes out. We need to take care of that, don't we? So, but we can do things like we can say, okay, there's 3 charges. I'm going to put my Gaussian surface around this space, and what's the flux through GS1? Sorry, this guy in the middle, and it would be Q1 over epsilon naught. And what's the flux over Gaussian surface 2? Well, it would be Q2 plus Q3 over epsilon naught. And then what's the flux through this guy at the end? That's 0. And you can see, these guys are going to be going all directions. So every arrow that enters it must leave it unless there's a source of charge there. So let's do this as a question. Let's get your clickers going. 2 coulomb positive charge sits at the center of a spherical surface of radius form 8 meters. Spherical Gaussian surface, I suppose it should say. Well, I said surface and surface, but think of it as a Gaussian surface. What is electric flux through that surface? So, what do you think? What do you think, class? I'm going to change my pen because I don't like that color. How are we doing? 9 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 people. Remember, as usual, if you're choosing not to use the clickers, just click something, so I'm not waiting for you. And so you can choose ether, whatever. I'm going to stop it in now. Okay. Let's see what everybody's saying. Pretty well everybody's saying A. So is that true? So I like to visualize. I'm a visualizer. So I have my 2 positive spherical Gaussian surface. I'm imagining all these field lines going off in. I'm going to draw 8 of them rather than the millions that I'm supposed to draw. And then what is the flux through the surface? I say flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And so I say, well, my flux is equal to, forget the E dot dA, my Q inside is plus 2 over epsilon naught. And I mustn't forget my units. When I write down a symbol, people tend to forget their units. It's newtons per coulomb times a meter squared. Oh, I didn't put down my units down here. Shame on me. It's going to be plus because it's a positive charge. If this was 2 minus, then all my arrows would come in. Yeah? All my arrows would come in. my flux would equal minus 2 over epsilon naught newtons per coulomb meter squared. So when the arrows are leaving your Gaussian surface, we call it a positive flux. When the arrows are entering your Gaussian surface, you call it a negative flux. So don't get, I want you to write this down every time, but we don't always use it, So don't get tied into this. Remember, all you need to know is the charge over the epsilon naught. And in a test, you could just simply put the numerical value down. Just a word about tests. A couple of people are just giving me homework to do when I grade your test. They're like not doing the calculation. They're laying it out, and then they're saying, you figure it out. And I'll do that for test 1, but test 2, I'm not going to calculate it. So you need to calculate things, and the only things you can leave are the constants like epsilon naught and ke and stuff like that. But pi's, I want you to calculate, and I certainly want you to calculate square roots, because if somebody else is making a mistake in that calculation, and yet you're not doing the calculation, it's not fair. So watch out for that. So not many people, but it's a couple of people, so watch out for that. So you can leave epsilon naught by all means, but work out the rest. Oh, let's do this one. This has got ijk. This must be incredibly hard because it's got ijk in it. So, well, if you visualize, not so hard. So my advice is you draw yourself a diagram. And what I'm going to do for those people who are at home, I'm going to pause the tape so that I'm going to stop it in a second. Okay. And what we get in, most people saying B, which is minus 5 over epsilon naught. So most people decided that it was inside the surface. So what do we do here? We say, I can say, hold on, my flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And so I know my Q inside. Well, I think I know my Q inside. I know my Q. But the question is it inside? That's the question. So then I say, okay, where is the Q? It's 2 on the X, it's 2 on the Y, and it's 2 on the Z. Oh, there's no 0. That's a very good point. That's bad teaching. That's exactly right. There's not a choice, so you could do it just by. That's one of the reasons why multiple choice are not easy to set up, because you've got to think of all the possibilities. So there's my charge. And then I want to do a different colored pen because I want this to kind of look decent. So pointer goes to ink color, goes to, we'll have nice light blue. And this is 4 on side, one bit on the origin and the other bit on there. So then we do that, that. And the question is, if I look from the side, I get that, where that's 0 and that's 4 in the X direction. And if I look at the side, I get that. So it is inside. So flux is equal to minus 5 over epsilon naught. And again, I didn't put down my units, newtons per coulomb times meter squared. Yep.
What's the application for this in real life? Like electromagnets?
I'm sorry?
Why would we use this in real life, just to get an idea of what this is?
Oh, we're going to do that next. Yeah, we're going to find electric fields with it. It turns out that this is a very economical way of finding electric fields in unusual circumstances. So it's got a purpose. It's got a very useful purpose, actually. And we get to that next, actually. So it's a good question to ask, why we're doing this, and it's a good question to ask, and this is useful. So we say, let's use Gauss's law to determine the electric field caused by a specific charge distribution. So I'm going to give you, we're going to do a dot to begin with, a point source, and then let's do a bowling ball's not the right expression. A solid sphere. And then we're going to do a hollow shell. And then we're going to talk about a infinitely long line. And I'm going to point you towards a, well, sorry, I didn't mean to do that. I'm going to point you towards a wall of charge. And all of these are done online on the homework help, you know, the YouTube thing. They're all done online. So I'm not going to do all of them, but I'll talk you through at least the beginning ones to get you going. So what we do is we say, okay, you're going to be given a charge distribution of some kind, and then it's up to you. Everything else is up to you. We're given a point of interest, and then you've got to do the rest. So you've got to decide what Gaussian surface will I use, and how do I get to this thing? And you're going to use Gauss's law. So throughout, we're going to say flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And if you think about it, you're going to be given a Q, and you know an epsilon naught, and you're going to want an E. So you're not going to be using this bit so much. You're going to be using these two on the middle and the left-hand, on the right-hand side is what we're going to be using. But how do we do this? And we say the value of the electric field is constant over the surface. We look for a Gaussian surface where E is constant on the surface, or E is 0. We say the dot product can be expressed. The dot product can be expressed as a simple algebraic product because E is parallel to dA, or I want E to be perpendicular to dA. I want either the angle between my E and dA to be 0, which gives me a value of 1 for the cosine. I want the angle between them to be 90 degrees, which gives me an angle of 0. I want it to either go away or be what it is. And then the electric field can be argued to be 0 over a surface. So the electric field is either constant or 0, and then I go for parallel or perpendicular E dot A's. And then we solve for E, so it sounds pretty straightforward. This first one I think is done. So we pick a spherical Gaussian surface centered about the charge. So basically we have this guy, there's my charge. I give you the point of interest. I say, there's my point of interest 3 meters away. And then you say, cunningly, sophisticatedly, you say, if I use a spherical Gaussian surface, which is centered on the charge, then I know that my E is constant. On the Gaussian surface. And I know that at every window, every little window, E is parallel to dA on Gaussian surface. So by me picking that Gaussian surface, I've done the two things I want from symmetry point of view. So I say we pick a spherical Gaussian surface centered on the point charge because for this surface E is parallel to dA, and for this surface E is constant. And we say, well, Gauss's law says, you've got to have Gauss's law down, so there's Gauss's law. And then we say, well, hold on, E's constant, so that can come out. So E surface integral of dA is equal to Q in over epsilon naught. Then we say, well, oh, it's a sphere. So the integral of all my little windows is 4 pi r squared. So then I say, well, let's just rearrange. So we get E is equal to Q in over 4 pi r squared over epsilon naught. And that's the correct answer, but it's not where we take it. We like to go back to KE in physics. So we say, well, KE is equal to 1 over 4 pi epsilon naught. So E is equal to, well, there's a 4, there's a pi, there's an epsilon naught. 1 over those 3 is a KE, so there's my KE, Q inside over r squared. Isn't that the equation we learned from Coulomb's law? Yeah, we've done this before. This is just redoing what we've done before in a different way, but we get the same answer. So that builds confidence. So, let me see. Yeah, nothing like reinforcement. Do that one, please. Okay. I just got a phone call, so I'm going to put this on Zoom recording. And so here we are. So basically what we have is we have a 10 coulomb positive charge. Let's get this. So we have a 10 positive, and it's at the origin, and use the method Gauss's law as shown in class to determine the electric field at a point 3 meters from it. So I don't say which direction it is, though I could say what direction it is. So I'm just going to picture this point over here. There's my point of interest. And then the rest is up to me. So I'm going to basically, so you can see which bit's which, I'm going to go through here. I'm going to go ink color. I'm going to go to something like light blue. And I'm going to do a Gaussian surface, which is there. And then what I do is I imagine a window, I put the window on the edge, and I say, well, that's my electric field because it's radial, and that's my dA because it's radial. It's going to be perpendicular to the window, and the window's the tangent to the circle. Then I say, well, flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. So flux is equal to, I better write down a few things. E is constant on surface, Gaussian surface, and E is parallel to dA on Gaussian surface. So I'm going to use the second one first, and I'm going to say, oh, well, that means the surface integral of E A cosine 0 is equal to Q in over epsilon naught. I just basically wrote this out in longhand, yeah, rather than having the dot product of two vectors. I wrote it out longhand, magnitude, magnitude, the angle between. And then I say, oh, and E is constant, so flux is equal to E integral, surface integral of dA. I'm sorry, that should be a dA. dA, which equals Q in over epsilon naught. And then I say, well, hold on. Surface integral of dA for a sphere is 4 pi r squared. So flux is equal to E times 4 pi r squared, which equals Q in over epsilon naught. We're almost there. So E is equal to 1 over 4 pi r squared times Q in over epsilon naught. Bring the Q, 4 pi r squared to the other side. And then I remember, oh yeah, Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Q in over epsilon naught, which equals, I look at my question, plus 10 over epsilon naught newtons per coulomb meter squared. Pardon?
What's the answer? That's not one of the choices.
No, you should.
Oh, so I just not worked out my. So I'm sorry. Yeah, you're right. So I need to go.
That's R squared, and then you need a.
Oh, let me think through it. I'm an old man. Let me think through it. So let's have a look. We had that. Ke. I substitute in for my Ke. I'm clearly using the value of Ke here. Did I do this right? No. Did I do that right? Oh, I need a Ke in there, don't I? Duh, what am I doing? Ke Q in over epsilon. Ke Q in over... Man. So, coming back here, E is equal to Q in over 4 pi r squared times epsilon naught. And then Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Ke Q in over r squared. Yeah, is that right? Sorry, yeah. Ignore all this. So that's going to be, what's KE? Times QN over R squared, which equals 1 times 10 to the 10 newtons per coulomb. Yep. So, not bad. Ignore that. Okay. Okay. I'm sorry? Oh, is it still going? What did people say? Let's have a look at that. Mainly A. Yeah, good. Okay. This is where it gets interesting. Imagine we have a solid mass of charge. So the space inside, it's not a point source of charge anymore, and the space outside. When you do Gauss's law, you can prove that E outside is equal to KE over R squared, where the R is measured from the center of the charge to the point of interest. It's not to the edge of the charge. It is to the point of interest. So as R gets higher and higher and higher, so the electric field falls off as an inverse square relationship. Isn't that just like gravity? Isn't gravity falling off as we go further and further above the Earth in an inverse square relationship? We could have used this technique to figure out gravity earlier on. This is also interesting. This is actually, if anything, a bit more interesting, which is we go inside. Now, as we go inside, we have less and less ground beneath us pulling us towards the middle, and more, charge beneath us, and we have more and more charge outside us. So if you think about it from an Earth point of view, imagine you're halfway to the center of the Earth. You've got a relatively little amount of Earth beneath you, and you've got a fair amount of Earth above you. So intuitively, what does that tell you about what's going to happen to little g as you go into the Earth? Isn't it going to get smaller because there's less and less matter pulling you downwards? And what would little g be at the middle of the Earth, when there's only matter around you and it's in all directions? It's going to be 0, isn't it? So that's going to, and if you look at these relationships, then where's my pen gone? Let's draw a diagram. If that's my charge distribution, and I plot a graph going from the middle outside, what happens is I get an increasing electric field because of R. It increases linearly as R increases, and then it falls off as an inverse square. Yeah, and that's what the Earth's gravity does. So if you were to dig a hole through the center of the Earth, when you got to the middle of the Earth, you'd float. It's like that. So this is just going to be, again, you're going to pick a spherically symmetrical Gaussian surface. You're going to basically have E constant. You're going to have E and dA parallel. And it's just going to be the same old, just like we did for the point source charge. It's just, in the end, you're going to look and say, oh yeah, it's a whole massive charge with value Q. So it's the same problem as the point source charge. It makes no difference. The radius of the charge, which is A, is not part of my equation. But this is not the same. This is different. So let's have a look. Yes, I determine the 2 meters from the center. Yes, this is the one I want. I'm going to go through this. I'm going to do this. So let's do a... Oh, I'm sorry. So let's do this. I'm going to go down. I'm going to go here. I'm going to go to purple. Sorry. Just a bit finicky on the pens. So I have a ball of charge, and that charge is 4 meters. And I have a point of interest, and that point of interest is 2 meters from the center. My point of interest is there. I want to find the electric field at this point inside the charge. So I'm going to change my pen color because I want to do a Gaussian surface. And again, I'm going to pick a Gaussian surface which is spherical and centered on the charge for the same reasons I picked before. And I'm imagining a window here, and my E is constant, and my E is parallel to dA. You see that? Your dA is always at 90 degrees to your little window, and your little window is a tangent to this sphere. So that's going to be radial. And your electric field is going to be radially symmetrical about the center of this charge, yeah? So those two things are going to be true. Then we say, well, flux is equal to, it's going to be the surface integral of E dot dA, which equals Qn over epsilon naught. And then I'm going to say, well, on my Gaussian surface, E is constant on GS. I'm going to put it down above it. E is parallel to dA on Gaussian surface, because that's the one I use first. So I say flux is equal to, well, let's have a look. This is the surface integral. This is the surface integral of E times dA times the cosine of 0 degrees. Let's make sure those are vectors. So this is going to be the surface integral of E times dA, which equals Qn over epsilon naught. And then flux is equal to, well, E's constant, so let's take E surface integral dA, which equals Qn over epsilon naught. And now I know that my area, the surface integral of a sphere is 4 pi. Now, got to be careful here. If you look back at the previous diagram, was it r we used to represent the distance to the sphere, to the center of to this Gaussian surface, or was it a? It was r, so r squared. And I would, if I were you, mark this, because what happens is people will often get the r and the a confused. Okay, because this guy here, that die there is a, and we don't want that. Cool. Okay. So this means that E times 4 pi r squared is equal to Qn over epsilon naught. And we've been here before, so E is equal to Qn over 4 pi r squared epsilon naught. I'm going to move that just because I want it to be nice. I'm just moving it. So E is equal to Qn over 4 pi r squared epsilon naught. And so remembering that Ke is equal to 1 over 4 pi r squared. Sorry, that's where I keep making my mistake, isn't it? Ke is equal to 1 over 4 pi epsilon naught squared. Yep, epsilon naught. Sorry. Epsilon naught. So then that means that E is equal to Qn over Well, KE times Q in over R squared. Same answer! I thought this was more interesting. Well, it is. Because what is Q in? Is Q in 9 coulombs? I don't think so, because if you look at it, we go, using our ink colour as our guide, that's 9 coulombs. That's 9 coulombs. And we're dealing with the inside of the Gaussian surface, which is not 9 coulombs. So we need to find a way of finding out exactly what is the charge that's inside our Gaussian surface. So I say, well, my Q inside is going to equal my volume inside times my volume charge density. So my Q inside is equal to, well, that's going to be, going in it. That's going to be 4/3 pi, and it's going to be R cubed because it's the inside, and that's going to be times, and I'm going to change my colour pen just to emphasize this so that it's like, really try not to make mistakes here. Q, which is for the total charge, over the volume of the total charge. 4/3 pi A cubed. Yeah? Because the R is for the Gaussian surface, so that's the small volume, and the A is for the charge, and that's the big volume. So then I do some, let's do the rest in black. So I'm going to go here, go there, ink, go here. So Q in is equal to the 4 pi's go and the pi's go. It's going to be Q times R cubed over A cubed. And I take that up there. And I say E is equal to KE times Q times R cubed over R squared times A cubed, which equals KE times Q times R over A cubed. So if I look at my question, I say, well, I can leave KE alone. I didn't have an answer for this. So in a test, I would leave KE alone. I would say my charge is 9 positive. My R, which is my Gaussian surface, is 2 meters from the center. My A, which is the radius of the ball, is 4 cubed times KE, which equals 18 over, not 16, 64. Is that right? Or is it 48? 64. 9 over something, KE. What does that equal? Sorry? Oh, don't worry about KE. Just give me in terms of KE. It's going to be, what's 18 over 64 as a decimal?
0.28.
So I'm getting 5 people talking to me once, which is very nice. But so what is it? 0.28.
125.
Just forget about the 125. 0.28 KE newtons per coulomb meter squared. Or you can give me a fraction. I can deal with a fraction. I'm just, the simplest fraction possible. Not 27 over the square root of 56, So, actually, no. Give me the decimal. Yes.
We wouldn't calculate out the exact value of KE.
So on a test, I would not, because I want you to just get on with things. So yeah, you'd give me the decimal, and you give me the KE. I'm happy for that. So what do you think? So here's what happens. I'm going to say using the method of Gauss's law as shown in class. I'm going to say that. And I'm going to look to see the following things. I'm going to look to see the following things. I'm going to look to see, do you have a decent diagram? I'm going to look to see, do you have Gauss's law? I'm going to look to see, do you have these things? I'm going to look to see, do you do this math right? I'm going to look to see, do you do this? I'm going to see, do you get to this? I want it. This is the physics. Sometimes people, they learn this and then they try and backpedal. It takes me a while, but I can always find it because there's steps missing. So don't do that. This is something, one of these Gauss's shapes is coming, so just focus on it. Learn the process. Do it right. Okay? But you know, when I ask it. I don't say what is. I suppose I could, and if I did say what is the electric field, then you can just use the equation. But you know, I'm certainly going to ask you a Gauss's law question, and it is going to say using Gauss's law as shown in class. Okay. Cool. Yeah, easy. This is just the same old, same old. Look at this. Let's go to there. Just look at this. Pen, color, light blue. Look at this. Oh, I don't want it. I will sort this out. I want a pen. Thank you. Look at this. You know, isn't this just like a point source of charge? It's just the charge inside over r squared. This is like the point source in charge. This is no big deal. If you can do the point source of charge, you can do this. What about this one? Oh, look. There's no charge inside.
Oh, because it's a shell.
Because there's no charge inside. It's a shell. There's nothing inside. So, oh, great. Okay. You get Qn is 0. So, looks like, oh, that's changing. Raises an interesting point. If I have this shell of charge and I draw a graph of E versus R, whereas before it was a linear increase until I got to the surface, and then it was an inverse square.
Maybe nothing, and then all of a sudden it's going to spike.
I mean, nothing.
Sure, and then you have a linear, really steep, right?
Well, it's like, it depends on the thickness of this thing. We won't even talk about it. It's the shell that's infinitely thin.
It would just immediately spike up.
Yeah, depending on how you want to model it. I mean, you know, if you want to model it with a thickness, then yeah, I think it would ramp up. You know, the main thing is that inside, no electric field. Think about that. No electric field, no force per unit charge.
That makes sense.
So you got charges on you, no force. No electric field, no radio station. No electric field, no body separating forces caused by electrostatics. It's a nice environment. And so they use this, they call it a Faraday cage, they use this to actually monitor, to keep people safe around high voltages. They use this all the time. Also, if you go inside a shell of a planet, you float.
Yeah.
So it's interesting. I don't know what this is my perverse mind, but I keep thinking that maybe the universe is a shell. And all our planets are floating inside that shell. I don't know. It's like, but it's kind of interesting. If you had a shell of a planet, there'd be weightlessness inside, gravitylessness inside, which just seems to me has been kind of like interesting. This next one, this is online. It's like, I want to talk. What shall I do? Shall I do it or not? We're behind. What the heck, let's do it, okay? Could be. So we have an endless line of charge. I want to know the electric field at that point there. So I come along and I define a Gaussian surface. Actually, there's a question on this on the next slide. Let's just get out of here. Yes. Using the method of Gauss's law as shown in class, draw, determine the electric field 2 meters from an infinite long positive string. So here's my infinitely long positive string, and there's my 2 meters from it. And then I change my colored pen to my nice sky blue for Gauss's law. And what I'm going to do is I'm going to use a sphere because I want to be symmetrical. Not a sphere, a cylinder. Because it has the advantage that the electric field here is going to be constant on the sleeve. You know what I mean by the sleeve?
Yeah, the surface.
And it's going to be well, it's not going to be 0, but it's going to be, and also here, E and dA are going to be parallel. But here, E and dA are going to be perpendicular. So I decided this thing, I either want E to be parallel to dA, I want E to be perpendicular. And so on the top and the bottom, E and dA are perpendicular. And what does that mean in terms of my E dA cosine theta? This will be E times dA, and this will be 0, because cosine theta is 0. Okay, so we'll get that. I say flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And I say for top and bottom, E is perpendicular to dA. So E dA cosine theta equals 0. And for sleeve, E is parallel to dA, so E dA cos theta is equal to E dA. And for sleeve, E is constant. So basically you throw away the top and the bottom because E is going to be perpendicular to dA, so it's going to have no contribution. So I say my flux is equal to, and you can kind of see it, the flux lines are the E lines, and they're going to go radially away from the wire, so none of them are going to go through this top surface or the bottom surface. They're going to graze it, and for that the flux is 0. So E is equal to, and this is going to be the surface integral of E times dA times the cosine of 0, which equals Qn over epsilon naught. So my flux is equal to E surface integral of dA, which equals Qn over epsilon naught. And I say, well, my flux is equal to E, let's E. Now, what is surface integral of dA? What is the surface integral of dA for this sleeve? It's going to be 2 pi r, that's the circumference, times, I'm going to call it L. So 2 pi r times L. So that's going to be 2 pi r times L, which equals Qn over epsilon naught. Okay, so we just take the E to one side, and that equals Qn over, let's have a look, it's going to be over 2 pi r L epsilon naught. Now, I believe in this one we leave, I'm going to cheat. I'm going to go back. I just can't remember for a second. We have that surface flux, and we have epsilon. Epsilon naught stays in there, yes? I don't go to KE in this one. It's just a little bit of its own. And what we do is we say, oh, I need to find QN.
No, you're looking at the wrong one.
Yeah, go back 2 slides.
Yeah, there you go.
Oh, KE is there. Thank you. KE is there. So I got to still do that. So, thank you. You just saved my bacon. So we say, okay, well, KE is equal to 1 over 4 pi epsilon naught. And I've only got 2 pi epsilon naught. So what can I do? I can say 2 pi epsilon naught is equal to 1 over 2 pi epsilon naught is equal to 2 KE. Agreed? Multiply both sides by 2. Agreed? So then E is equal to 2 KE QN over, that 2 goes, that pi goes, that epsilon naught goes, over RL. Agreed? So then I say, oh, well, my Q inside is equal to that amount of charge. And for this, I have to give you the amount of charge per meter somehow. So Q in is equal to L times the linear charge density. So Q in is equal to L times, well, lambda, the linear charge density. So E is equal to 2 KE L lambda times R over L. So E is equal to 2, let's do it, 2 KE lambda over R, which equals 2 KE. Lambda in this case is 6 over R in this case is the distance from the thing, which is 2. So E is equal to 6 KE newtons per coulomb meter squared. And that's done on homework, on that homework helpline. If you follow what I'm doing, it's the same process all the time. It's just, it's got different letters, different numbers. If you follow what I'm doing, that's what I'm doing. This guy, it's on the homework helpline, but I never get to it. So we won't talk about that, okay? One of those Gaussian surfaces coming up. You've got 2 minutes. Last little thing. The electric field lines always go perpendicular to the surface, and on rounded surfaces we have nicely spread out Gaussian field lines because it's a low electric field. Electric field lines, and near a point we have a high electric field. So, for example, needles are great for spraying off electrons. They're great. And we use that to our advantage in many circumstances. Good old Benjamin Franklin invented a lightning rod which had pointed tips on. Not to be outdone, the English scientific community said, we already invented that. They hadn't. And they said, we'll just make it different but similar. So they the idea of a lightning rod is not that it gets struck by lightning and is a good conductor. The idea of a lightning rod is it discharges the house. So you want a tip so the electrons will leave it. As the ground becomes negatively charged and the house becomes negatively charged, you discharge it so the positive charge cloud does not notice it. This is the worst kind of discharging. So this puts a nice conductor on your roof, which then has a charge on it. So that tends to attract lightning. And there's so much current in a lightning bolt that it will tend to damage the wire and not burn the house down. So back in the day, Benjamin Franklin really knew his stuff. I'm going to stop the thing there.